This is a final year project on the development of feature engineering tool for multivariate time series by student Kang and his supervisor, Associate Prof. Madhukuma. The bulk of this final year project is focused on establishing relationship between events. When we talk about smoker, we will normally associate the disease that is related to them. This includes lung cancer, heart disease, and even stroke. We associate this disease to smoking because they are prevalent in most smokers. But have we considered the other factors at play? Genetics, secondhand smoking, carcinogens? Association by correlation is very intuitive because we simply establish a relationship from what we know. Action A relates to action B, but one event doesn't necessarily cause the other event to take place. Correlation and causation are often confused because the human minds like to find patterns even when they do not exist. Causation explicitly applies to cases where action A causes outcome B. On the other hand, correlation is simply just a relationship. There are three components in this final year report. The first step is to identify and implement the different possible causality tests. The second step is to identify the prerequisite that is required. This is because not all datasets are suitable to run the causality test. Lastly is to translate the whole project into a GUI toolkit that is readily usable. The causality related feature that will be introduced will be Granger Causality and Transfer Enthalpy. Granger Causality is tested in the context of linear regression model. Looking back at the example of lung cancer and smoking, when we try to analyze the inclusion of genetics into a regression equation, does it make the forecast better? How do we actually know that the forecast is better? Since a linear regression model is used, the cause matrix can be identified as a variance of residuals. Does taking genetics into consideration lowers the error significance? That is to say that genetics contain useful information in forecasting, which allows for equation 2 to generate a result better than equation 1. If the error is significantly smaller, we make the conclusion that genetics significantly impact the risk of lung cancer. However, the selection of our primary variables are critical in the causality test. On top of smoking, should we consider secondhand smoking and carcinogens? These are critical factors that will impact the results of our test, and this needs to be taken into consideration extensively. This next section is on transfer enthalpy. If we say that Granger causality is tested in the context of linear regression model, then transfer enthalpy is tested in the context of enthalpy. Enthalpy is under a branch of information theory, which is the scientific study of quantification, storage, and communication of information. The intuition for enthalpy is that it is the average number of bits required to represent or transmit an event drawn from the probability distribution for the random variable. It can also be seen as the average level of information, surprise, or uncertainty inherent in the variable's possible outcome. Instead of linear regression in Granger causality, we look at enthalpy and mutual information in transfer enthalpy. When we look at the enthalpy share information of lung cancer and smoking, conditioned upon the previous value of lung cancer, we get the transfer enthalpy value of smoking to lung cancer. After looking at the different features, we need to take into consideration what are the prerequisites before running the test. Since Granger causality and transfer enthalpy requires our dataset to be stationary, we will look at the various tests to ensure stationarity in our dataset. We could individually run stationarity tests on each variable using the augmented Dickey-Fuller test and conclude that the system is stationary. Or we could complement it with a Johansson co-integration test and directly make the conclusion that the system is stationary. The last stage of our final year report involved generating the front end and back end for users to interact. The back-end server is served using a Python Flask since most of our library to run our tests or feature engineering are reliant on Python. The front end is served using Flutter since it offers a large variety of beautiful material design choices. They both communicate using a HTTP RESTful API. Putting everything together, firstly, Granger Causality and Transfer Enthalpy is implemented first. However, to ensure data readiness, a set of stationarity tests are also included in the system to ensure reliability of our causality tests. Lastly, the toolkit is glued together using Flutter and Flask. Thank you for your time, and this is the end product of the final year report.